All right. So we talked about electrical fields and we talked about voltage. Now we get to talk about both of them together. So what could be more exciting than that? Try and wrap up all this. Uh, oh my God, it's the maps again. We got more topographical maps. So we want to link these two ideas together because they're really important. And we're going to go back to the idea of topographical maps for a minute because I think uh, this helps us out. It makes it a little easier to understand. So if I have a topographical map, um, and we said, this is our lower point, right? And this is up on top of the mountain. Here we're in the valley. If you've done any hiking in mountains, you know you don't go straight up the hill, right? That requires a lot of force. It requires you to do a lot of to move up the hill very quickly. Instead, we do a zigzag course, right? So we go up the side of the mountain by doing switchbacks. Um, why are we talking about this? Well, the orange path to get from blue to red requires a lot of force, right? We got to push hard with our legs to get up that steep slope, but it's much shorter. The purple path doesn't require as much force from our legs, okay? But the path is much longer. As it turns out, the work and change in energy is the same. Why is that? Well, because we know the potential energy is defined only by our elevation, right? So as long as we don't have any losses, if we're not talking about no frictional losses, my elevation here determines the potential energy difference between red and blue. So no matter how I get there, if I don't have any frictional losses, I did as much work on my body as any other path. Okay, it just happens in different ways, right? This is big F times little d. This is little f times big D. Okay, and they both equal work, and they both equal that delta PE, which is defined only by how high you are at the end of your trip. Okay, so what does this have to do with electrostatics? Well, electrostatics works in the same way. Okay, the work required to get from one voltage level to another is the same no matter what path you take, right? So if I have a certain voltage at the center of my electrical field here, I can go straight there, right? Big F, little d, or I can take this nice spiral, not quite a switchback, but a nice spiral to the center, which is going to be a little f times a big D, right? Here I'm working directly against that electrostatic force. Here I'm sort of side skirting it, but I'm traveling a long way to get there. This is just like traveling up our mountain here. Okay, the orange path is straight. The same amount of work is done along the orange path as it is along the purple path. And the difference in potential energy of my charge when it gets to the center is going to be the same. It's going to gain the same amount of potential energy. Now we're going to do the same thing we did before and divide this equation by Q so that we can get a sense of not what happens if I take this particular charge, but what happens per unit charge that I move from here to here. And so I'm going to divide this equation by delta Q, or by Q, and do a little algebraic rearrangement. You may not notice this, but we've seen that before, and we've seen that before. This was our definition of electrical field, and this was our definition of voltage. Isn't that exciting? Watch this, watch it. Oh, nope, sorry. Watch it, there it is. So there's our voltage, that's delta V, the change in voltage. That is the change in potential energy per unit Q, right? Like the elevation from 0 to 10 meters. It tells me how if I move from point A to point B, how much potential energy I'm going to get per unit Q is equal to our electrical field times delta S here, and that delta S is the same as D. It's basically your path length, where you've walked. And so we can write the change in elevation, delta V, from 0 meters to 10 meters, is equal to how far you walked times the slope of your path, which is E. Okay? The slope of your path is kind of like the slope of the path here, right? This is a really steep slope with a short delta S. This is a really shallow slope with a large delta S. Same here, large delta S as we swirl around, but I'm going up slowly from look how long it takes me to get from one equipotential to another, right? I have to go all the way here. That's like climbing from 0 to 5 meters, right? It takes me a long time to get there. But ultimately, the change in possible potential energy is going to be the same. And that's what voltage is. So voltage from here to here is always the same. Okay, but the electrical field might be different depending on what your path is. Oh, and there's our nice image of the hill. So this is if we're climbing this mountain, right? One of them we just go straight up the hill, the orange line. The other one we sort of swirl around and get up there slowly. Voltage is the difference between this and this. Electrical field is the slope of the path that I'm taking. For a point charge, we can use that relationship to find the voltage field around a point charge. And with a little math, this leads to an equation that looks like this. So the voltage around a point charge is K times Q over R. Now notice that R is not R squared as it is when we talk about Coulomb's law. Okay, but it does say that the farther I get away, the farther I am away R, my voltage is going down. Okay, so if I, let's say I was at 10 meters here, right? I might be 5 meters here and 2 meters here and 1 meter here and 0 meters here. It still has, it's basically describing that elevation on our nice little hillside, right? This is 10 volts. This is halfway up 5 volts. This is like 2 volts. This is 1 volt. It's just like elevation.